tonight we're seeking all these semi-prime positive integers that are solutions to this equation. Let me write down what I mean. P and Q are the standard letters for primes, not necessarily distinct. Now, notice something very interesting right here. This is what we call a semi-prime, and again, this is the type of form we're looking for to be a solution to this equation. Now, notice something that's kind of nice here with respect to sigma, which is the sum of the integers of the sum of the divisors, the sum of the divisors of a particular integer. Now, notice if we consider p plus 1 times q plus 1. Expand this out, we get pq then we get p q and 1. Okay, but those are precisely because p and q are relatively prime. PQ is certainly a divisor of itself. That's n is a divisor of itself. P is definitely a divisor. Q is a divisor, and so is 1. But notice that this is equal to sigma of n. It's the sum of the divisors. Okay, so a fairly simple form for the sum of divisors of a semi-prime. Now, so let's go on down here and see if we can solve this problem. We know what sigma of n is. Also, tau at n is just the number of divisors. Again, the distinction, sigma n is the sum of the divisors of n, and tau of n is just the number. And it's clear that there's just 4 of those. Okay, very, very clear that that's the case. And so what happens when you simplify this equation by replacing this object right here with 4, we get sigma of n is equal to 180. Okay, now what's important right here is just to physically substitute things. Okay, we have this statement right here, sigma of n is equal to 180. And so we've already seen that p plus 1 times q plus 1 is the sum of the divisors. Okay, so at this stage, it's very important to write down all the divisors of 180. So towards that, we actually compute the prime factorization. It's clear this is divisible by 5, 2, and also 3. The sum of the digits is 9, which is divisible by 3. Now, notice right here, and this is related to the tau function actually, but that tau, and I'll write tau of 180, even though it's not, let's go ahead and write this down. Tau of 180. That looks like a T, doesn't it? Okay, but the number of divisors is just what you get when you increment each of these exponents. So that would be 3 times 3 times 2. Now this isn't a bad thing to write down. This is equal to 18, right? So there's 18 divisors, but that means there's 9 divisor pairs. Okay? And so if you'll notice right here, there's a lot of work went in right here. I didn't want to waste the time with you having to watch it, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9 divisor pairs. And we're just equating what we just discovered to be the sum of the divisors with each of these divisor pairs. Now notice right here, this would imply that p was equal to 0, which of course is absurd. We are looking for semi-primes, right? And and then q is what, 179? Now that may well be a prime number, right? Who knows? Q is equal to 179. So you see, we're hunting for circumstances where both p and q are prime, because that'll give us the semi-prime condition we're looking for. Now, it doesn't happen here because you would get 1 and 89, and 1 by convention is not a prime. Right here, you would get 3 and 44, and you have to go all the way down here where you get P is equal to 2, Q equal to 50. Now, if you don't trust me, check the others. Okay, so this is our first semi-prime. That would correspond to N equals 118, right? 118 is considered semi-prime. It's almost prime. It's the product of two primes. It's the next best thing. And that means its formulas are fairly easy. Okay, now right here, you would get P is equal to 5, which is prime, and Q equals to 29. And of course, this would induce the semi-prime 5 times 29, which is N equals to 145. And those are the only two I got. Now, I didn't check it out for, you could actually consider PQ being the same thing, P squared or Q squared. Go through that. I didn't mess with that. I just did the quote, the true semi-primes. I think the definition of semi-prime, they're not required to be distinct. But in any event, these are the two solutions I got when you took P and Q to be distinct. Okay, N equals 18. Down here you get 17 and 9. Right here you get 8 and 19. Some stuff that's close, but these are the only two where both of the values are actually prime that I got. So anyway, I did get, what was the question? Find all semi-primes solutions. Well, I get N equals 18 and N equals 145. So N equals to, what was it, 118 and then 145. I'll put comma 45 here. Notice these two values would be kind of hard. If you're trying to guess and test your way through this, it'd be rather tough to guess these 3-digit numbers, right? So this form here, it's very nice, methodical, and exhaustive. And it's this part right here of writing down the number of divisors of 180. This is the number of divisors, which let me abbreviate that. Okay, this is the number of divisors abbreviated. It's kind of nice to know. If you have a small number, you know when you've exhausted all the divisors. But for a number like 180, it's not. You may not know right off the bat that there's 18 divisors. Okay, but this formula proves it, taking the product of each of the exponents incremented, because you have to allow for an exponent of 0 to account for factors of 1 along the way. So that's what happened right here, folks. And again, the analysis reveals these are the only two semi-primes. And you may want to check it out for P squared. I'm not sure. I didn't check that. But there's nothing in the definition of semi-prime that says P and Q have to be distinct. So I may well have lost. There may be a P squared that satisfies this. I didn't check. All right, that's all. Thanks for viewing.